So why the strength of student is very less today? I see only 85 students around. So it seems like all are in a mode where they are not paying attention in the class. So from this lecture, I will be more strict about the attendance. So also convey to your friends that even if it is online, you need to be regular in class and pay attention. Also, the kind of things that we are going to discuss now in last couple of lectures and the lectures to follow would be a bit tricky or complex to if you try to do it yourself. So that way also it is good to attend the class so that you get an idea in class itself and your searching time or reading time would be reduced. Yeah, with that, let us begin with. Actually, I want to start a new topic today, but I think Urjit has asked about revision of this latent Dirichlet allocation. He had some question related to algorithm or equation, I guess. So I will not spend more than 5-10 minutes. I will give you the idea once again. And then if there are any issues still related to algorithm, maybe during the lab we can take it and in lab we will see with the example that how actually it works. Is this clear? Is this okay, Urjit? Okay, so let me quickly give you the idea, just in case any of you have missed it. So in topic modeling, we are saying that we have a Word document vector where there is a relation between document and Word. And now with LSI and PCA, we said that this is very syntactic process and it doesn't exploit the underlying semantics, that relation between the words, relation between the document are not exploited there. So that idea led to this technique called topic modeling, where you look at the topics of the document rather than the words of the document. So you say that this document is about certain topic rather than a document with list of words. Yes, screen is not presented. Okay. Okay, because I was just revising, but anyway, let me share the screen. So the idea is that to analyze a document, you look at the word, but actually while you're looking at the word, your focus is on topics, what topics the document talks about, and then you make relations between words, between documents, and between topics. So the topic modeling talks about this triangle of word, topic, and document. How does it work? It says that a word can belong to a word can represent multiple topics. A topic can have multiple words. A word can be part of multiple documents, and a document contains multiple words. So this is many-to-many relation, which we defined as multinomial distribution, and conjugate prior for that multinomial is Dirichlet distribution. That's why the name is Dirichlet. And the topics are not observed. What we observed here is word document vector, and from that we want to calculate topic word and topic document relation, or topic word and topic document metrics that we want to calculate from that. So topic is not observed or is unknown, hidden, and that we call latent. So that's why it is a latent Dirichlet allocation, because the multinomial distribution that we are talking about, the topic word and topic document, is latent because topics are not known. So we say that the topics are coming from an unknown Dirichlet distribution, parameters for which we want to find out through our data. So that is one unknown. And second is document to topic relation. How the topic is distributed across the document. is also unknown because topics are unknown. So that comes from another display, another multinomial parameterized by beta. So we have defined two parameters, eta and beta. Latent topic parameters and alpha is latent topic parameters. So these two are unknown distributions from where topics are coming and topics are distributed across the document. And then we look at the word and we want to assign topic to a word. For every word, we want to assign a topic. So that is the word topic relation that we want to calculate. Parameters Z is the document, right? D is number of document, N is number of words, and Z is topic, capital W is word. So for every word we assign a topic, and eventually for every document we assign set of topics. This is how this generative model is defined. And we said that this is generative, so actually instead of calculating the exact probabilities, we can do it with GIF sampling and rely on GIF sampling to generate the word topic distribution. The reason being that to collect a large set of text and to assign a topic manually to every word is very cumbersome task. It takes a lot of effort to prepare a supervised data set to solve the problem in a generative way. So what we do is we make use of GIF sampling, which we had discussed with the Bayesian network, approximate inferencing, a similar algorithm, but now your model is changed. The graphical model now is different. And we say that every word is a random variable. Right? Every variable is a random variable of this Bayesian network, some underlying Bayesian network. And the word to topic relation that we want to figure out is, if you see the split notation, ZWL in a square bracket. So every word and every topic is a random variable. And we say that the topic generates words. That's why the arrow is dependencies from topic to word. And this rectangle says that it happens n times for every word. For every word you have to do it. So that's why this split of rectangle, we call it split diagram, so that's why this split, otherwise this rectangle. A rectangle which says that for every word you need to assign a topic. So topic word dependency is shown by this arrow. So your algorithm will iterate n times for every word. So start with every word, and for every word, calculate probability of k different topics assigned that can be assigned to the word. So outer loop is from 1 to n, inner loop is for 1 to k. This is for one document. If you want to do it for D documents, then again the outermost loop is from 1 to D, document 1 to D. Within the document for every word 1 to n. Within the word, for every possible topic assignment 1 to k, assign a topic to a word. Right? This is how the loops are structured in the algorithm. And what we do inside this assignment, how we make this assignment? So we, in GIF sampling, we start with a random assignment. So first randomly assign some topic to word. So every word has some randomly assigned words, which we have seen last time. This latest news article, speaking at Panchayat Aaj Tak, Punjab CM Channi said, "हमारी सर्कस है तो बंदर का रोल है," and all this political, what do I say, all this political unnecessary things. Okay. So for every word, randomly assigned topics. So let's say T1, T2, T3, T4 are the topics assigned. There are a list of say five topics, T1 to T5, which I randomly assign to every word. And then GIF sampling will pick one word at a time and reassign a new topic to that word. So starting with this random assignment, speaking at Panchayat Aaj Tak, Punjab and all that, Now, in first iteration, very first iteration of the algorithm, I will take out speaking, and I will think that given that all other assignment of word is correct, which topic should be assigned to the word speaking? Right? Are you with me, Urjit? So now I want to decide a correct topic assignment for word speaking. Assuming that all other words are assigned the right topic. So I will use the formula of probability of word given topic and topic given document. So I will look at my document. I will see that how many times the word speaking occurs and how many times the word was assigned topic T1. So I would say that speaking occurs 5 times, and out of 5 times, once it was assigned T1. So 1 by 5. Another parameter that I can look at is how many times the T1 occurs within the document. So T1 occurs 1, 2, 3, 4, maybe 6, 7 times in the document, let's say. And out of the 6, 7 times, how many times T1 occurs with speaking? So that can be 2 by 6, 7. So joint probability of observing speaking and T1 divided by number of times occurs document. So inside the document, how many times you have seen T1? That can be a multiplier. So these things we can directly count from these words. I will not repeat the formulation again because there are some parameter discussions which I do not want to go into again. But this is how the numbers are counted, and based on this count, we can reassign probability of speaking. Now, once the probability of speaking is reassigned, look at the next word and repeat the process. Say that assuming everything, all other words has correct assignment, what can be the best topic assignment for word at, then for word panchayat, then for word arts, then for word sak, and so on. Keep on repeating this for n number of words until you reach to a stable assignment. This is characteristic of this sampling, that if you repeat the process sufficient number of times, maybe 1,000, 10,000 times, then eventually it will reach to a stable assignment which is true to the underlying distribution. Right? So this is how it works. And we also talked about these two vectors. So the input is word document vector, from where we want to calculate two output vectors, word topic and document topic vector, that we can calculate after running this process for thousands of times. Right? Is this structure clear to Urjit and everyone else? In case if you are not comfortable with the display or underlying probability and formulation, please ignore this for a while. During the program, we will see that how actually it works. So programming wise and counting wise, it is very easy. But otherwise, is the architecture is clear? Okay, I think Uzi says yes. Okay, so this is the structure. And maybe next lab we'll run the program also, so you will know how exactly it works. So if there are no other doubts on this, we will move to the next topic. Again, a very interesting algorithm, and it is also grounded in probability. So now we are talking about unsupervised learning. Again, the principal component analysis, latent semantic indexing, and latent derivative allocation. They were also unsupervised learning algorithms. And primarily they are dimensionality reduction techniques, but we also know that they can also be used. a clustering tech. We say we are actually doing is probably the algorithm that we are going to discuss today. Probably one of the very first probabilistic unsupervised learning algorithm, and we can actually map it to more popular unsupervised. Okay, I think voice is breaking in between. So maybe I got some message in between, so that's why the connection might have been lost. But is this clear now? Am I audible now again? Okay. So maybe the device with which I'm connected, no, so if some message or call comes in between, then temporarily the voice gets broken. Yes, so the algorithm that we are going to talk about are unsupervised learning algorithm. Actually, we are doing this since last 3, 4 lectures. LSI and LDA, all three of them are unsupervised learning algorithms. Primarily, they are dimensionality reduction techniques, and we have studied them as a dimensionality reduction method. But most of you would have realized by now or would agree that this can also be used as clustering techniques. For example, LDA, the topic modeling that we have just discussed, divides the document into various topics. So that is a kind of clustering method. So what we are going to talk now for next few lectures is clustering methods, some other clustering methods. And we will start with a very important and very basic clustering algorithm known as expectation maximization algorithm. This is one of the very first uh, probabilistic clustering algorithm, and roots of this clustering algorithm can be found in many modern algorithms like k-means and k-middles and other distance-based clustering methods. We will see that also. But for now, let's begin with expectation maximization algorithm. It is a general framework actually. It is a general framework of clustering algorithm, and you can model different kind of algorithms using this expectation maximization framework. K-means is, of course, as I said, one of the special case of expectation maximization. But first, let us relate it with our knowledge of Bayesian network and try to understand it with the perspective of Bayesian network. So the story of Bayesian network that we have seen so far is there are a number of random variables x1, x2 up to xn, which can take some values 0, 1, and so on. Most of the time, for the simplicity of calculation, we keep this variable binary, but we all know that it can also be multinomial. So given these random variables x1 to xn, which can take values 0, 1, and so on, during our discussion of Bayesian networks, we did two things. One is we designed the network. Design network means modeling the dependency between the random variables x1, x2, x3 in the example that you can see on the screen. Parameters for the network that we have designed. So in the example on the screen, the parameters are probability of x1, probability of x2 given x1, and probability of x3 given x1. These are the three parameters. And our task is to learn these parameters, and now on we call this parameter theta. Let's say all these parameters are part of a parameter vector called theta. So we want to learn this theta from the data. So we look at the data, we calculate this theta, and our parameters are ready, and then we can use the network for inference. And this is what we have discussed so far. The simplest case of naive-Bayes classifier and more sophisticated case of Bayesian network. Now the question is, what if the data is not complete? The input data on which we are training the network, what if it is not complete? And here I am showing you three cases of that. So case one is where some random variable values are missing. In this example, x2 has missing values. Case 2 is where some data items are missing. So for example, the first data has both x1 and x3 values missing. And case 3 is where the class label is missing. So some random variables, no value is observed for some random variable. So for example, in the right side of your table, case 3, x1, x2, and x3, the x3 is not observed at all in any of the data items, D1 to D3, x3 is not known. So if this is the case, then how do we deal with such situations? That is the question we ask. So case 1 and case 2 are case of missing data. Case 3 is case of hidden variable or latent variable. Why hidden variable? Because when I say the entire attribute is missing, entire x3 is missing, what I am claiming is x3 is there, but it is not shown in the data set. Because it is not observed, it is hidden or latent, and I want to find out x3 given what I have observed, that is x1 and x2. So that is case of hidden or latent variable, and this is useful in when you make this assumption of case 3 that there is one attribute which is not observed. It is not there. It is not part of the network, but it is there. Sorry, it is not part of the data set, but it is there. This is the assumption you make. Then you are talking about unsupervised Bayesian network learning. The learning that we have discussed so far is called supervised Bayesian network, where all the data points are observed. Now I'm saying that some data point is not known, and if that data point is class label, then you want to do the labeling task in unsupervised way. You do not have a prior label in your training set, but still you want to do it. So that is called unsupervised learning. So we'll focus on this today to set up the ground for unsupervised learning. So let's call this latent variable h. Let us call this h. And the parameter that we want to estimate is theta. So what is our probabilistic question that we usually ask? There is probability of x comma h given theta. So we calculate theta from the data given. So data is combination of x and h. So we want to calculate probability of given the set of parameters theta. Here now the variables are divided into two categories, x and h, to distinguish between observed variable and hidden or latent variable. So x stands for all the attributes or variables, random variables, which we are not observing, and x stands for all the variables that we have observed. Right? Are you with me so far? Any questions on this? I'm waiting for a minute to get the answer, just to make sure that you are all following what we are discussing. So is this clear? Dev says yes. Okay, so in our original formulation, it was probability of x, where x stands for all random variables x1 to xn, and some class label c. Instead of that, now I'm saying that we want to calculate choice distribution of x comma h, where x stands for all the random variables which are observed or for which the values are there in the data set, and h stands for all the random variables which are not observed. So those random variables for which values are missing in the dataset. And we want to calculate this joint probability. And the parameters by which this joint distribution is defined is called theta, the underlying parameters that we want to find out. So this is our setup. In or compared to the previous Bayesian networks that we had discussed, the difference is that in previous case, the data was observed. All data points were observed. There was no H in your data set. So probability of theta given X. So you look at the X and you calculate theta. You find out value of parameters and you say that the model has been trained. On the contrary, now here you have a chicken egg problem. To calculate theta, you need to know all the data points, or you need to know value of all random variables. But here, some random variables have missing value, that is H. So the data that you have observed is not sufficient to calculate theta. And to make prediction, to calculate the value of missing variable, what you need is theta. If someone gives you the parameters, if someone gives you probability, you can calculate value of random variable. This is what we have done all the time during inference, right? When we are discussing inference, we say that if some random variables are given, if conditional probability tables are known, then we can calculate value of unknown random variable. So if someone gives you theta, you can calculate H. And if someone gives you H, you can calculate theta. Right? So a kind of chicken egg problem, or also I think you should be able to see the loop here. There is a loop between theta and H. Given H, you can calculate theta. Given theta, you can calculate H. And what kind of parameters that and we want to do it in a way that we can predict the value of missing data given X and theta, and we can calculate theta given X and H. If you are paying attention and if you have understood what I am saying, then you would know that we have all the necessary tools to take the discussion forward. I think Utsav has raised hand. Do you want to ask something, Utsav? Or was it unintentional? So if you, okay, you say by mistake, no problem. So I think if you are paying attention and if you have understood this thing properly, then you know that we have all the tools and all the background ready to take the discussion forward and imagine that what would follow. Given our background of Bayesian networks and the latent display allocation that we had just completed, the algorithm should already start running in your mind that how would you do this, right? There are two unknowns, theta and H. If you know H, you can calculate theta. If you know theta, you can calculate H. So can someone tell me where is this going? What will be the next step, or what will be the next thing that I would say? How would algorithm start? Of course, we will take the advantage of the fact that Bayesian networks are generative models. Dev says use gift sampling. Yes, so you're on right track. This is what I was expecting, but it is not exactly gift sampling. But that idea of gift sampling that generates sample and then iterate and come to a stable situation, that would be applied here also. And we want to do it in a way that maximizes the joint probability of X and H. So we want to find out those value of H for which the likelihood of joint distribution XH is maximum. So that is the probability of theta given XH. And from your algorithm course, you know that when we want to maximize something, we use the notation argmax theta. So how do I read this? We want to find out those value of theta for which this joint distribution of XH has maximum likelihood. In more simple language, it is find out theta that best describes distribution x comma x. And this is what the algorithm does. The algorithm called expectation maximization algorithm. Expectation maximization, I think you would also be able to guess where the name came from. What does expectation mean in this case? Can anyone answer? You need to be a bit, you need to think a bit from your algorithm course. Expectation is expectation of the random variable. In our case, h. Right? So we want to calculate expected value of the random variable h. We know that a normal variable we calculate mean or average. For random variables we calculate expectation. So expectation is find out the value of h, and we want to maximize this expected value. So that's why the algorithm is named expectation maximization algorithm, where expectation stands for expectation of the hidden variables. And while calculating the hidden variables expectation, we make use of observed variable x and parameter theta. So probability of x given x comma theta. But then theta is also unknown because theta we calculate from the data. So how does the algorithm work? Algorithm works with first random initialization of theta 0. Something that we was talking about. So randomly initialize the parameter. Let's say theta 0 is coming from is chosen randomly. And then iterate over this process until you get the maximum likelihood of probability of theta. So given the initial value of theta, we can easily calculate the value of x and h. So we have the data ready. Given some random theta I, we can find out the value of h, and now the entire data set is ready. Once the data set is ready, recalculate, re-estimate your parameters theta. So given that all the data is observed, you can always calculate theta again. So calculate theta back, and once the theta is updated, again go back and calculate new value of x, and keep on repeating on this until you reach to a stable distribution where there is no further update in theta or there is no further update in value of h. So you will reach to a maximum value of p theta x h, where the algorithm would stop. Let us take an example. Let us say this is the Bayesian network given to us x1, x2, x3. And these are the value of random variables. x3 is not observed. So x3 is our hidden variable. So I have put h in the bracket. And there are only 4 examples to keep things simple: E1, E2, E3, and E4. And the model is described by this parameter: x3 given x2, x2 given x1, and probability of x1. So how would the algorithm work? The step 1 is initialize theta 0. So first randomly initialize theta 0. Theta 0 means 3 probability values: x3 given x2, x2 given x1, and x1. So x1 is 0.8, x2 given x1, x3 given x2 is this distribution, and x1, x2 is this distribution. So let us say this is our initially randomly initialized parameters that we call theta 0. Now if this theta 0 values are given, can we calculate the value of x3? Answer is yes, we can calculate value of x3 by putting this parameter value as per the conditional probability table. So the step 2 is expectation step, or the step where we calculate expectation of the random variable. In our case, the random variable is x3. So what we want to calculate is probability of x3 given x1, x2, theta 0. And formula also we know it is joint distribution of x1, x2, x3 divided the probability of x1, x2. Now, what are these values? First, let's simplify this as we did many times before, and it reaches to this value. Now, what are these values? Probability of x3 given x1 into probability of x2 given x1 into probability of x1. And these values are from theta 0. So, whatever assumption we have made for theta 0, those values we will put here. It will turn out to be 0.8 into 0.3 into 0.8 is equal to 0.192. Similarly, for other part of the equation, if you want to note down, I can wait for some time because I'm not spending more time on this because we already discussed this many times. But I will put it on screen for 1 or 2 minutes. If you have any questions, you can ask me. Right? Simple. So in the denominator, we marginalize over x3. Point 2 and probability of x3 is equal to 1 given all this is 0.8. So between 0.8 and 0.2, we will select the value of x3, so which is here 0.8. So now there are two variations in this algorithm. One is soft version, second is the hard version. So in soft version, you put 0.8 as a value of x3. In hard version, you put 1 as value of x3 because you are doing hard classification. So you take only one value of x3, either 0 or 1. So put x3 is equal to 1. Right? But let's say it is 0.8 for us for now. Or let's say we are doing hard version. That would be simple. So let's say we are doing hard version. So we will make x3 equal to 1 because that probability is higher. So that is computation of step number 2, where we are calculating recalculating the x3. Do it similarly for all value of all examples. Take it for all examples and you get value of x3 for all combinations of the data points. So calculate for first example 1, 1, 1. Calculate for second example 0, 1, 0. Calculate for third example 1, 0 and you will get 0. For fourth example 0, 0 and you will get 1. And so on. So just I'm assuming that this will be the final computation. So in the second step of the algorithm, you calculate expected value of hidden variable. So that you do for all examples. So this will be repeated for all examples in data set, and you have h value given. Now once this is calculated, what is the next part? Re-estimate the theta. So once you have all this calculated, next part is re-estimate theta. Given the value of x and x. So given the new value of x1, x2 and x, you update your conditional probability table. And this time it will be 1 by 2, that how many times x1 was true out of total example. Then x2, x1, that is x is 1 by 2 and so on. So re-estimate and you get the new value of theta. Then again go back and calculate new value of x and keep on iterating. So if you keep on iterating like this, ultimately you will reach to a probability distribution which is stable and for which the likelihood is maximized. So this is the small example of expectation maximization algorithm. Right? You try this yourself now. Try to complete this calculation for E2, E3, and E4. First example I have calculated. Similarly, calculate for second, third, and fourth. We have some time, maybe 5 minutes, so you can look at the computation and also please ask me if you have any doubts on this. Is everything clear? Are there any questions? Can someone confirm? Any questions? I am not getting any reply. If there are no other questions, I will end the session here. Okay, I think Sale is asking each channel explanation can complete 8 items. Yes. So depending upon the number of random variables and out of those random variables, how many hidden that we need to see. So if there are 4, x1, x2, x3, and x4, and only one of them is hidden, then for every of these, you need to calculate its hidden value for every example. So for any example, if there is a hidden value, you need to calculate that hidden value. In this case, there are 4 examples. That's why E1, E2, E3, E4. Okay, then if there are no other questions, we will end here. And from next time, we will talk about more clustering algorithms. And probably in this lab also, this coming lab also, we will talk about implementation of LDA or expectation maximization algorithm. I will end here. Thanks.